Okay, got it. All right. Good morning. Weird sharing this screen, but like I said, I wanted to show you guys that it's called a sampling distribution. So that's what we're going to develop. So I just want to show you how to use it or not, just to run through it and see what's going on. So I posted it on our Moodle page. And if you click on it, it's just going to be a text file, and that's fine. So what you can do is you can just copy all of this, copy, and then open up your RStudio, which I have here. And because this is just R code, you can open up an R script if you want, or you could open up an R Markdown and paste it into an R code chunk, but that's a little bit more, I don't know if you're going to write about it, which you might want to, but for an R script, it's just going to look like this, and then you can just paste it in there and you'll have something that looks like mine here. Just as a side note, I did change the name or the naming convention. I used camel type instead of underscores because the textbook uses underscores, but then that didn't copy and paste directly. So I would have had to go in and enter the underscores. So to save you that trouble, I just changed the names instead, which is fine. So remember the example that we talked about yesterday, and we had this idea of, okay, so if we know that 88% of adult Americans, I think it was, support some, I can't remember something. I wish I could remember what it was. I think it was something to do with energy. It doesn't matter. So 88% support, and so 12% don't support, right? And so what we can do is, well, if we know that there are 250 million American adults, if we wanted to recreate this, then what we could do is we could get R to do that for us. So one thing we can do is we can define the population size. Now, if you wanted to change this population size, you can do that right here. So that's a benefit of defining it up top, so that you can just change the population size once and then it'll follow through. Notice that when I hit this pop size, it highlights where it shows up later, right? And that's in case you need to change something, if there's a typo or something like that. Okay, so we've got this pop size, the population size is 250 million. So then what we're going to do is we're going to create these possible entries. And it looks nasty, but if you kind of break it down, so inside the C, we use the C to concatenate, to put together. So whenever you want to join stuff up, often it's using a C. And then the rep command just says repeat whatever I tell you to do for some number of times, right? And so here we're saying repeat the word support 0.88 times whatever the population size is, right? So 0.88 is 88% of, in this case, 250 million, right? And then repeat not, so repeat the word not for 12% of the population size, okay? So what you can do is you can run these commands, right? And by running the commands, I mean transferring the commands from the R file, right, where we've saved them, to the console down here. So the console is the thing that actually runs this operation, right? And so to run it, so to run a line, you can have there's lots of ways that you could do it, but my usual way is just to have the cursor on the line that I want to run, and then I hit Command Enter. And so here, oh, I've blocked my own view here, the chat. So here you can see the population size, right? So now we've defined the population size, and it's 2.5 times 10 to the power of 8, which is 250 million. So then what if I run this possible entries command? It has to think a little bit because it has to do what? It has to generate 250 million things. And maybe I shouldn't have done that. Nope, there it is. Okay. And it should come up over here. There. 1.9 gigabytes. Yikes. You'll see I got away from that. I didn't want to do that, but we can do that, right? And so it just generates support for 88% of 250 million times, and then not for 12% of 250 million times. So we can do that. We can generate this population, right? And we can simulate. So that's what we're doing. We're simulating the population. So then what I can do, there's a sample command. Now I can sample from different distributions or different populations in this case. And so what I want to do is, if I want to sample 1,000 people, like we said, we could write support and not on pieces of paper and throw them into a bin. And then we could take a sample of 1,000, right? That's what we were trying to do. And so that's what we're going to try to do here. So now I'm saving it and I'm calling it the sampled entries. I use the sample command. I need to tell it where to pull a sample from and what size, how many. Okay. And this is without replacement. So if I run this, I get my sampled entries show up over here, and what I sampled was support, not support, support, and that's all I can see for now. That's okay. You can look at them, but there's no point really. We understand that it keeps going from 1 to 1,000. So then if I want to count how many were in support, right? We know that the parameter we're trying to estimate was 0.88. So it's kind of backwards because we're starting with knowing what the population proportion is. And then now we're trying to figure out what our sample proportions might look like. Okay. And so if we can use the sum command, and here a little bit sneaky, we use the double equals. So that's going to be basically saying wherever the sample entries are equal to support, right? You can sum those up, right? How many satisfy that logic, right? So we've got this logical command, and then divide by 1,000, and that's going to get us our proportion. So here, our sample proportion was 0.875. Now, if I sampled new entries, okay, so what I'm going to do is I'm going to run the sampled entries again. And then I'm going to find the sample proportion. This one's bang on, 0.88. So then what I can do is I can run the sampled entries again. Right? Every time I run it, it generates a new sample every time. Right? And so then I can find the sample proportion. So 0.875 was a little lower than 0.88. 0.88 was just perfectly bang on. I can't believe we saw that, but that's okay. And then 0.883, a little bit higher. That's just how it goes. So what we're going to see is that these sample proportions, oh, that's got to be confusing if you get 0.88 the first time. Man, oh man. Yeah, what am I doing here? Yeah, so everyone's kind of hovering around 0.88, right? And so that's what we're going to see, and that's how these things behave. And so if we want to do this 1,000 times, so we run the sampled entries, compute the sample proportion, we run the sampled entries, compute the sample proportion, we're not actually going to do that 1,000 times, especially because these values that you're running, right, the 0.88 that you got, the 0.858, my 0.875, the 0.88, the 0.883, we're not storing those anywhere. So that's a problem, right? Because we want to be able to see these later on. And so I'm going to show you how to do that. And it's just a fun exercise. It's not something that I expect you to develop, but it's nice to have seen it. And if you ever think, oh, I want to do that again, maybe in a different scenario, then you've got kind of some base code that you can tweak instead of having to build it all from scratch, right? And so I just want to show you how it works, because it can be really useful to have this for loop, it's called. And if you don't have any background in programming, that's okay, but it helps. but it's okay, you'll survive. Okay, so if I want to do this 1,000 times, so collect 1,000 sample proportions, right? So maybe I'll add that here. Collect 1,000 sample proportions. Notice how I use the comments to make comments to myself, right? And you. But they're not going to be run when I run the code, right? It only does the stuff that isn't green. So what I'm going to do is I'm going to define this n, and I'm going to force it to be 1,000, right? So n is going to be the number of times that I run this thing. And looking here, I should be using an arrow. I'm old school and lazy, so I tend to use the equal sign sometimes, but I'm trying to be good and use the arrow, because we should use the arrow. There's like a small number of times when the equal sign messes things up. Usually it works, and I haven't come across a time when it doesn't work, luckily, or else I would have learned my lesson. But we should use the arrow. Okay, so if I define my n to be 1,000, I'm going to run that. We can see n is just stored here, and it's 1,000. Okay. Now, when we generate values, we need some place to store them, right? So we need to tell them where to go. And so that's kind of a tricky thing, is because we need to create essentially an empty column. Okay, and so I'm going to call that my sampling dist. Okay, and what you do is you repeat NA, so you repeat an empty block n times. So again, I've defined n up here so that I can change it and I can tweak it. Okay, but if I do this, it should generate a sampling dist down up here. And it says that it has 1,000 entries and they're all NA, it looks like, which is what we told it to do, right? And so now what happens is now I can fill those NA spots, right? I can replace those empty spots with values. Now, one thing that's kind of, I don't know, it makes it kind of fun, also kind of annoying, is that if you're running really kind of huge code, it can take a long time for it to run. And so sometimes at work, it would take something an hour to run. And so, you know, you're working on other stuff, but really you're just waiting for that code to run, which is really kind of a weird idea, but also kind of cool. So remember how long it took to generate this possible probably, I haven't tried it. So I have my go-to ways of doing it. You could probably, yeah, I mean, we're not doing anything fancy. I have no idea about hardware or probably software. So I don't know, but there is code that, and you could, so I'm pretty sure Python would run through this a little bit faster, for example, right? But it's not the end of the world. But for us, so I could show you, I changed the population size to something really small, so 2,500. And then I changed the number of sampled entries to be 100. So I changed my sample size to be 100. Confusing because we have a sample size that we're pulling from basically our vat of supports and knots, right? And then we have how many times do we generate the sample proportion? That's not really going to be our sample size, but it kind of is. It's a sample size of sample proportions. So in terms of the sample size, it's going to be how many entries am I pulling each time. I feel like I was going to show something over here, but now I can't remember. Oh yeah, remember how the possible entries, it took quite a bit for it to generate this 1.9 gigabytes of entries. It's huge. So that's why I changed it, but you could change this here. This should be 25 million. 1, 2, 3, 1, 2, 3. Oh, of course it's lagging. Who knows if it got all my zeros. It's not thinking about anything, so I don't know why it's, oh, nope. 1, 1, 2, 3, 1, 2, 3, right? So that one should be that size, but honestly, no. Right, we're going to get what we need out of 25,000 or 2,500. And then so again, what I'm doing is, so I've generated this for loop. So for I, so we have this placeholder I in 1 through n is how we read this. Okay, and we need to have these curly brackets that close up. So we're doing this for loop. Okay, and so the population size I'm saying is 2,500, and then I'm generating these possible entries again, and they're just based on the population size. So notice how I just grabbed this same code from up above. And then I need to generate the sampled entries. Okay, and here size should be 1,000. But just to save us some time, I just changed it to 100 instead. And I just noticed a typo here. I didn't change this one. That should be 100. I'll update the code, but that I posted on Moodle. Hey, that was a sloppy oversight. Anyways, so what happens is, let's see here. All right, so we do the sampled entries. Okay, again, we use that sample command, sample from the possible entries. So now I only have 2,500 possible entries, and I'm pulling 100 of those, right? And now I am generating the sampling dist, and then the square brackets tells it which slot to go in of sampling dist. So sampling dist square bracket 1 is the first slot, sampling dist square brackets 2 is the second slot, 3, 4, 5. And so here I is looping through 1 through n, right? And n was 1,000. Oh, maybe it is. Sorry. We are looking at 1,000. It wasn't an oversight. Whew. I was surprised that I had missed that. Okay, so I think we're good. Yeah. So now what I'm going to do is I'm going to highlight this whole for loop, including that end bracket, because otherwise it won't know when to close up. Okay. And what we're going to do is I'm just going to use Command Enter. Size at 21 is showing at 100. Oh, at line 21. Oh, so it should be 1,000, but because I didn't want to wait forever, I changed it to just 100. So yeah, so I did some tweaks here just to show you what's going on. So now that this has run, and you can tell that it's finished running here because we have this caret down in the console that's ready for another command. So then it's finished running. So then if I go over here and 0.092, sorry, I guess it should be 100. Why am I saying that? Because these are all too small. Anyways, I'm not going to run it again because it takes a little bit of time. Or maybe I will. How about this? I'll run it there. Because these values, I don't know what's going on. I need to caffeinate, I think. That's always the problem, right? Okay, so here, these values are closer to what I'm expecting to see, right? And so, so that's good. So now I can look at things in the sampling distributions, right? And so what can I do? Now that I have the sampling dist data, so I've just done it 1,000 times, and it just calculates the sample proportion and stores it, and then we can look at the distribution of the sample proportions. So what can we do to visualize the distribution? Well, I can look at a histogram. So what I typically do, and it's just kind of hanging out here, I always write my code somewhere where I can save it, right? Even if you don't end up using it. For example, if I do the histogram of sampling dist, sampling dist, right? And I run that. So notice how when I type it up here, I can save it for later and I can use it later. Whereas I find that when a lot of people are beginning, they just want to type it down here, the histogram of sampling dist. But then it's gone forever, right? So if you type it up here and then run it from your code, then that's going to be a lot easier, because then you don't need to go back. You can go back into your history, right? And it'll tell you all the things that you ran, and you can copy paste whatever worked, right? But that's not very good, right? That's not in the long run. So here, if I want to do a histogram of the sampling distribution, well, now I have it twice over. I'm going to remove this. Then I can go up here and run that little bit. So here, what we see is this beautiful normal distribution. Okay, and I can do things like I can calculate, bump it up a bit. I can calculate the mean of the sampling dist. Oops. 0.88218. That's really close to 0.88, which we know it's supposed to be, right? And so the standard deviation of the sampling dist, oops, 0.031333735, right? So we have this mean and standard deviation. We did do some tweaks here. We changed the population size to be really small. And then we also just pulled a sample of size 100. But if you ran it with the proper numbers and changed it here, match the sample size. Okay. So if you ran it properly with 250 million for the population size and a sample size of 1,000, we would get even closer to a center of 0.88 and an even nicer looking normal distribution. So, okay, I'm going to save this because I'll post this code. So this new code, I'll replace that one on Moodle, but it's there for you if you want it. All right, so now I want to talk about this a little bit. So I'm going to stop sharing here. How do I do that? stop sharing this and start sharing this. Okay. Hey, I didn't set it up. That's okay. I'll just change the name later. Okay, so we saw through the simulation in R, we saw using the simulation in R, and I'll say updated code posted on Moodle, but I'll post it after class. Obviously, you haven't seen me do it, so it's not done yet. But I'll say updated code posted on Moodle. So we saw using the simulation in R that as we collect a sample of sample proportions, okay, that as we collect a sample of sample proportions, okay, so that's going to be an important kind of concept here. The sample of sample proportions, kind of confusing, right? The distribution of the sample approached a normal distribution, okay? And so the distribution was approximately normal. I'll put a little exclamation mark because that's cool. Okay, so what does that mean? Remember, we can use the normal distribution to find probabilities, right? That's a big deal. As long as we have a mean and a standard deviation, we can use the fact that it follows a normal distribution to find probabilities. Okay, so as long as we have the mean, which I showed you, we can find easily, right? As long as we have the mean and standard deviation, we can use the fact that it follows a normal distribution to find probabilities. We can use the fact that it follows a normal distribution, to find probabilities. Right? How do we do that? Using z-scores. So here, using z-scores. Exclamation marks all over the place here, right? And so pretty cool development, right? That, okay, so even if we're talking about a proportion, so a proportion is, the percentage of yeses or the percentage of no's. So those are proportions, but if we collect a large enough sample, then those proportions are going to be coming from a normal distribution. Okay, and so what happens is this is called the central limit theorem. Okay, and so the central limit theorem This is the basis. This is the base, or basis, I should say, I guess, basis of the central limit theorem. Oops. Okay. The central limit theorem, we usually just abbreviate CLT. I'll write it out sort of properly here. Central limit theorem, so the CLT. Now, the central limit theorem says that as we collect a large enough sample, right, and this is to calculate one sample proportion, okay, then that sample comes from a normal distribution, or that sample proportion is going to come from a normal distribution. So the central limit theorem says, the CLT, the central limit theorem, says that as long as our sample size is large enough, and we'll talk about what do we mean by is large enough, right? We need to specify how large is large. We've seen that before, right? We've seen that with the binomial, the normal distribution, the normal approximation to the binomial, right? And it's actually the exact same thing, right? We've got yeses and nos. So we've seen this before. We just haven't called it the central limit theorem. So the central limit theorem says that as long as our sample size is large enough, which we'll define, but it's also, we've seen it before, the sample proportion will have come from an approximately normal distribution. Okay. What's the mean? With mean P. Okay, remember P is the population proportion. We saw that in our histogram, it was centered on 0.88, right? And we expect all our values to be around, oh yeah, so we'll talk about what it is. It depends on what P is actually. So that's, if you're trying to detect a really small proportion, then you would need a really large sample size. Whereas if you're only trying to detect a 50-50 split, that's kind of the smallest sample size that we would need for 50-50. Now I'm eating my words here. Anyways, we'll look at some different scenarios. So the large enough stems from the proportion that we're trying to find. So with a mean of P and standard deviation, the standard deviation is going to be the square root of P times 1 minus P. Now, typically, right, 1 minus P, I usually just write Q, but here I want to emphasize that it's actually the same value all throughout, divided by N. Okay, but this, we're going to rephrase we're going to call this the standard error instead, just because the standard deviation doesn't really work here, right? And so just we call this the standard error instead, because it's taking into account the sample size down here. Remember for the binomial, we said it was the square root of NPQ, right? That was the standard deviation. So now we've switched things up a little bit. And so we actually call this the standard error. We call this the standard error of P hat. Because P is going to have some, sorry, I don't want to get derailed because I'm running out of time. Anyways, can talk about it all day. But so this is the standard error of P hat. Okay, and so P hat has some variability, as we saw, right? Every P hat, so every sample proportion that we pull is going to be some spread from the population proportion. So what we say is we say that P hat follows a normal distribution with a center of P and a spread of P times 1 minus P over N. Okay, so this is the sampling distribution. Sampling distribution of P hat. Our mean is now the probabilistic chance of having observation. Sort of. The mean is the population proportion. The problem is we don't know what it is, right? In our example, we did because we wanted to start and say, okay, pretend it's 0.8. Then how can we guess that it's supposed to be 0.8? Right. And so we kind of started knowing what it was, but in reality, we're not going to know what P is. So that's going to be tough. Right. And so what we do is we say, okay, well, I'm trying to figure out what this P is. Right. And so then if I know that P hat comes from a normal distribution with the mean of the population proportion, that's going to give me some idea, right, of what this P is. Okay. And so I think that addressed it. So we said the CLT will hold if the sample size is large enough, right? So if the sample size is large enough, okay. So what we say is that, okay, for it to be large enough, then we need to have at least 10 successes and 10 failures in our distribution. Okay. So what we say is we need n times p to be more than 10 and n times q to be greater than or equal to 10. Okay. And so this is the success failure condition from the binomial, or from the normal approximation to the binomial, right? And so we've already seen it, we've used it, but here it is in kind of another scenario. So the success failure condition from the normal distribution, normal approximation to the binomial, right? So we've seen that before. The problem becomes, and here I'm just going to make a note that Q is just 1 minus P. I'll expect you to be on top of that from now on, right? Kind of a it's a quick swap. But if you prefer 1 minus p, you're allowed to write that, but I prefer q. So here, the problem is that we just said we don't know what p is, right? And so the problem here is IRL, in real life. We don't know what p is. So what can we use? We can use p hat instead. So we use p hat instead. Okay. So what this becomes is the difference between using n times p and n times q. This is going to be the expected number of successes and failures versus using p hat and q hat. That's going to give me what? The observed successes and failures, right? And so here, this becomes the expected successes / failures. And then, so when I use n times p hat has to be greater than or equal to 10, and n times q hat has to be greater than or equal to 10. This is actually just the observed successes and failures. All right. So now you can look at your sample size and you can look at your number of successes and the number of failures. That might be given in the question. You don't necessarily have to do the calculation, right? But if you only have n and p hat and you don't have the number of successes over n, which is how we get p hat, it kind of depends on the information that you have. But so now what we're looking for is the observed successes and the observed failures has to be at least 10 each, which means our minimum sample size would be 10, right? So this means the smallest possible sample size we could consider is 20, right? And that's if we have an even 50-50 split, right? 10 successes, 10 failures. But if you're looking at 2 successes and 18 failures, you would need to increase your sample size until you've reached at least 10 of each, right? So it depends on what the proportion is, right? If you've got a really small proportion, then you're going to need a large sample size to make up for that, to be able to see those small proportions. Okay, and so another condition that we need to check for the central limit theorem to hold is that our observations have to be independent of each other. Okay, and so another condition of the central limit theorem is that all observations must be independent of each other. Is that all observations must be independent of each other. Independence, well, we know the definition of independent. It means that the probability of one thing doesn't depend on anything else happening, right? So knowing that I'm in the sample, does that affect the probability of you being in the sample, right? And so if it doesn't, then we can say that they're independent, right? And so this is and I'm gonna go a little crazy here. This is saying that the probability of A given B is just the probability of A. What? We were done with that. I know. We were and we weren't. There's a reason we have to talk about it, right? And so two events are independent if the probability of A, given that B has happened, is just the probability of A, right? A doesn't care about what B did, right? And so then the probability of A is just on its own, right? And so it is going back to that, that independent situation from probability. So we are talking about that. But what we can do is usually, and what we assume, so here's kind of to the rescue. Okay. We assume that a randomly selected sample will guarantee independence. Okay, and so what we're actually going to end up checking is, did we collect a random sample? Yes or no, right? And so we assume a random sample will ensure all observations are independent. One last thing that I want to just make sure. One last thing, and this is optional because it's pretty rare that it's going to be a problem, but the optional situation that we could check out is that the sample size, so the sample size that we're pulling, should be less than 10% of the population. Okay, the sample size should be less than 10% of the population. To do what? So we're taught that, okay, bigger samples, that's good, right? And it is good, right? The larger the sample that you can have, the better. But once we start exceeding 10% of the population, then we start seeing dependence, right? We lose that independence. So to ensure the observations are independent. So in shorthand, N less than 10% of the population is what we would be checking, right? I'm going to say that this is optional, right? If you want to show off, you can include this one as part of your argument for independence. But our main argument for do I have independent observations is yes, I do, because I collected a random sample. And then the alternative, so the optional addition there would be, yes, I collected a random sample and my sample size is less than 10% of the population. So I feel comfortable assuming independence. And I'm all out of time, but these Friday classes, what a way to start the day. If you have any questions, let me know. Otherwise, we'll keep going through chapter 5. So I encourage you to read ahead so that when I say it, it's not the first time you're hearing it, because this stuff can get pretty picky. So, but we'll keep going through chapter 5, section 5.2 on next week. Can't remember when we meet. If you have any questions, let me know. Otherwise, I hope you have an awesome weekend. And you have assignments due tonight. Okay, bye.